Okay, section 3 here, vector equations. This is not a difficult section by any means, but there's definitely some terms you're going to want to make sure you become very comfortable with because we're going to use them a ton throughout the semester. So a vector is just a list of numbers. That's all it is. A matrix with one column is just called a common column vector, excuse me. Right? And the order does matter, right? Note that 4, 7 is not the same as 7, 4. Right? The set of all vectors with two real entries is denoted R2. Okay, so again, we should know this symbol, right? That's the real numbers, real numbers. Boy, my handwriting is just so awful. Real numbers. So all this means is this is a vector with two, this is the number of entries. So, you know, it's kind of this situation here where star is a real number, okay? So you can think about it also as points in the plane, right? If you look at the Cartesian coordinate, really it's the real number crossed with the real number. So some basic stuff. Let's say we have a couple of vectors, u and v. How do you add vectors? You just add the corresponding entries, right? So u plus v would be 2 minus 1, which would be a 1, and then 1 plus 3 would be 4. And then 4u would be the same as 4 times 2, 1. You have to multiply everything by it. Okay, basic operations there. As a matter of notation, you can list it this way or this way. I will almost exclusively use that way. This, however, is not correct. Okay, these are different sizes, right? Row by column. So this is a 2 by 1. This is a 1 by 2. So these are different. So I already kind of gave that away, right? What's a geometric description of R2? Well, if R2 are 2 points that are real numbers, they're really points in the plane. Okay, so you can think of a geometric description as being the Cartesian coordinate system. What do vectors from R3 look like? Well, R3, right? The 3 means there are three entries, right? A, B, C, where A, B, and C are all real numbers, right? So what's the geometric description then of R3? Well, instead of points in the plane, you can think about it as points in 3D space. So you'll have to excuse my artwork here, but if I were in the classroom, right, I would say we're in a room, and then if you point to the corner of the room, you can call that the origin, and then you could pick a point in space determined by an x, y, z. And so a geometric description of R3 would be like, points in space. R4, you can add time to it, and then it just gets nuttier from there. Like you can do it in general, right? So vectors from Rn are called ordered n tuples, and they're represented by n by 1 column matrices. We're going to talk about Rn a lot. It's not immediately obvious what a geometric description of Rn is. I think once you get past 4, points in space, 3D space, and add time to it, it gets a little bit messy, but you can talk about them in general. So they're just, we'll be talking about Rn, which are just ordered n tuples. Okay. So here are some algebraic properties of Rn. Okay, so these are u, v, and w are vectors in Rn. So they're vectors with n entries, column vectors with n entries. And c and d are scalars, meaning just numbers. Okay, now these may seem immediately obvious, like no kidding, right? U plus v is v plus u, right? That's called the commutative property of addition. Duh. Well, maybe with real numbers, but not so much with matrices. So we're going to see where some of the things that we take for granted are not immediately obvious when it comes to matrices. These are all properties of Rn, so you can deal with these, and they all have their names, right? In terms of distributive, associative, zero vector being the additive identity. There's you can think about it as an inverse, right? There's left distributive and right distributive. That's the multiplication. And then there's a multiplicative identity too, right? We're going to talk more about that, but these are the properties of Rn. So this is important. You want to pay attention to this. Given vectors v1, v2, all the way up to vp in Rn, and scalars c1 to cp, if you take a look at this vector y, which is just c1 times the vector v1 plus the scalar c2 times the vector v2, etc., this is called a linear combination of the vectors v1 to vp. And these c's are the weights, right? The scalars or the weights. Okay, we're going to be talking about linear combinations a lot. So first question, is B, right? And again, these are from what? These are clearly from R3, right? These are vectors with 3 entries. So is B a linear combination of these 3 vectors, A1, A2, and A3? In other words, can you find some, I'm calling them x's, right? Can you find some scalar x1, x2, and x3 such that x1 times this plus x2 times this plus x3 times this gives us B as a result? Is that possible? Well, I mean, this is if we want this situation here, which is what we're asking, right? Does this look familiar, right? We just have an augmented matrix. Is there a solution? If there is, the answer is yes. If there isn't, the answer is no. This just means equivalent. So I'm not going to take the time equivalent. I'm not going to take the time to do all the row reduction like we did before. You can actually do that on a calculator or your computer in you know, a matter of seconds. You should know how to do it by hand, but I don't expect you to do that. You can use a calculator going forward. These two are row equivalent, right? So if this is true, right, what does this say? This is augmented, so we have this situation we called before, right, a free variable. So what are the pivot columns? That's a pivot column, that's a pivot column. So those are the basic variables, x1 and x2. x3 is free. The answer is yeah, it is a linear combination. And how many answers are there? An infinite number. Okay. Now, when this happens, this free variable situation with R3, there's other stuff that goes along with it, but we'll get to it a little bit later. So again, you want to definitely pay attention to this part. We're going to use these ideas and this nomenclature a lot. Okay, so you have a V1 to VP, so these are vectors in Rn. If we take a look at the set of all possible linear combinations of those vectors, that's called the span of V1 to VP. Okay, and is clearly a subset of Rn. Technically, it's a subset of Rn generated or spanned by the V1 to VP vectors. Okay, so the span of V1 to VP is a collection of vectors that can be written in this form with C1 to CP, any scalars you like. And we say a vector B is in the span if B is a linear combination of V1 to VP, right? So that's really what I was asking here, or another way I could have asked this question is B in the span of A1? So is B an element of the span of A1, A2, and A3? And the answer is yes, it is. And you can find the actual x1, x2, and x3 that make that so, but we already saw there's a solution. So that's another way to ask the exact same question. Of course, the zero vector has to be in the span, right? Because if you can choose any constants you want or any scalars you want, if you make them all zero, guess what you get? Zero. Zero vector is always in there. Span is never empty. It's got at least a zero vector. It may have only the zero vector, but it's got at least a zero vector. So let's think about this, and I don't think I want to say anything. I think hopefully someone brings it up as a topic of discussion when we go over this, because I think if you understand this, that's good. So if we have non-zero vectors in R3, right, U and V is not a multiple of U, they're distinct, what is the geometric description of the span of UV? So I'm not going to give that one away. I want you to think about it. I want you to think about what that means for U and V, what it looks like, what it's generated by, what this creates geometrically. Okay, it's a good question. Again, here's the worksheet. I'll post the key for it. So here I asked it a little bit differently, right? Is B a linear combination? It's the same as saying is B in the span. And then here again, of course, is the homework corresponding to section 3.